So in this final work example, we'll look at a force field that's going to be working on a particle that moves on a straight line from one point to another point and then another segment to a third point. So we'll have to set up those paths ourselves. And in this case, the force field, or the integral, is actually given to us already in differential form. And so this is often done if the components of f are p, q, and r, then we can write it as the integral p dx plus q dy plus r dz. And it's customary like this to not put the integral in front of each term, and also just to like forget about putting the parentheses around the whole expression. So it just looks like this guy right here. So y dx plus z dy plus x dz. So here this would be the vector field y comma z comma x. All right, so let's get cracking. So what are we going to need to do? As usual, we'll need to set up our parameterization. So I'm going to have C1 be the first curve. So C1 of t is going to be parameterized by, and let's see, so we need to go from 2, 0, 0. So I start with 1 minus t, 2, 0, 0. 1 minus t times the point that I'm starting at, plus t times the point that I'm finishing at. 3, 4, 5. And so putting this together, I get 2 plus t, 4t, and 5t. So that's my path. Let me just tidy that up a little bit. It's bugging me. There we go. And then for the next one, so for the second path, C2, we'll have 1 minus t, and this time we'll be starting from 3, 4, 5, and then we'll be going to 3, 4, 0. So just going straight down until we hit the xy plane. And so this one is going to look like 3, 4, and then 5 minus 5t. And whenever we do this type of path, we know that you're going to get there in 1 unit of time. So this is both for 0t to 1. Okay, so, and I guess I can write down my derivatives. So C1 prime is going to be 1, 4, 5. And C2 prime is going to be 3, 4, oh sorry, what am I doing? It's going to be 0, 0, minus 5. There we go. All right, so let's see. So for our integral over the first one of y dx plus z dy plus x dz, we are going to have the integral from 0 to 1 of, and then I've got 4t times dt plus 5t times now 4 dt, and then plus, and I've got 2 plus t, that's my x coordinate, and then dz is 5t dt. And so just in case there's any question, this 4t dt is coming from 4 dt. Oh, sorry, I said 4, I meant to say 4 dt. It's coming from 4 dt here. And this 5, yeah, that shouldn't be there. That 5 dt is coming from here. Okay, and so then I can work out this integral, and I get some number. Hooray, 49 over 2. Awesome. Okay, then my other integral, and let me just be lazy and copy that sucker. So this is once again going to be from 0 to 1, and now I'm going to have 4t times 0 dt plus 5 minus 5t times 0 dt and 3 times minus 5 dt. So I get a little bit of something right there at the end. And when I integrate that, I get minus 15. So that tells me that the integral over the entire curve of f dot dc is the integral over c1 plus c2. So that's the integral over c1 plus the integral over c2, which is just a long way of writing out that I need to combine these two terms, and I end up with 19 over 2, I think, if I did the arithmetic right. Okay, so there we go. I guess the point of this example was to show how this breaks down, right? That you can totally do this. If you have one long complicated path, you can break it up into two paths, and then that separates into two integrals. So that's always a useful thing to do. Probably, if I'd asked you to do this problem, you would have done that even without thinking or blinking, just automatically, because, hey, it makes sense, right? The other thing is that I just want to go back and kind of look at what happened here with these. These guys zeroed out because of that part right there, yeah? And so what did we see happen here? Well, this is a thing that happens in more generally. So for x, dx is x prime of t dt. So on a horizontal path, so in other words, when c looks like only the x coordinate's moving, the y coordinate is some fixed constant y naught here, then what we have is ds is just ends up being x prime of t dt, which is dx. So the integral of some scalar function ds on such a curve ends up being the integral just with respect to dx. And so you can see sometimes components will drop out depending on the direction that the curve is moving in.